Thank you for the invitation. And well, I feel, in all after the talks that we have experienced from Greg and Rob, and I would like to get you through also the work that we do at TU Darmstadt regarding adding some geometric and structural inductive biases in robot learning in different problems that we try to solve. And a bit of motivation about why am I interested in structured learning. If we look at humans, we see that even from a very early age, humans perceive in order to act, and they act in order to perceive in a continuous perception action cycle. And through these interactions, they build their sensory motor coordination, they build a representation of the world and then models about the world. And in particular, why does it move? Wait a second. It's stuck. Some technical problems. Yeah. And we use these representations to interactively explore and learn skills. Now, the question is why geometry, why structure? I think already we have seen some very impressive results in different scenarios. But again, if we take inspiration from humans, we would see, and also general biological systems, we would see that there are many references also coming from cognitive science, where they show us that biological systems can only interact with the world when judging accurately the 3D scene level topology, but also object level poses and sizes, which are interestingly mapped in different areas in our brains, in the cortex. And it's also very interesting to understand that animals and humans use projective geometry to map these 3D scenes to retinal images. This doesn't work now for some reason. Let me see. Okay. And to understand what they are viewing, animals and humans have a constant experience with the consequences of the geometry. And this forms our understanding about 3D world and actually object level information whenever we interact closely with some objects. Now, whether these geometrical operations are innately embedded into our brains or acquired by experience into a long time, it is a point of discussion and debate, and there are many different philosophies. So we make the hypothesis, I think also in this workshop, that if we build in specific geometric and structural inductive biases, we can have more efficient and more generalizable learning. And this is exactly the premise that I like to work on, what I call structured robot learning. Well, we know what robot learning is, but I strongly believe that if we deploy the structure of the problem, geometry and physics, we can enable faster, safer, and more scalable learning of robot behaviors. And I think very nicely, Robert also talked about the large models currently. However, it is not clear what kind of representations they extract and how well you can abstract a 3D world, whether we can really disassociate high-level topological information from pure structural information about objects, so that we can also generalize beyond the data that we see, something that humans we know are very, very efficient in doing. So in this talk, I will go through some of the works where we will talk about different types of geometrical, if you will, neural representations that allow us to do some nice reinforcement learning, how we can coordinate different objectives that can be embedded in a C3 space, and eventually how neural representations can allow us to do active acceleration for mobile manipulation. So it's a collection of works. I don't know how much in detail I will go right now, but I guess we can discuss also after in the poster session the questions. So one important aspect when acting with among humans and also considering complicated systems like mobile manipulators comes when we consider safety. And we have tried to figure out how we can use the topology of the constraints in order to act safely. One of the approaches that we use in robotics in order to define, for example, obstacle avoidance constraints is using deep sign distance fields. So early on, we were very interested into using these neural geometric representations like the deep sign distance fields in order to learn articulated object representations of this distance field that give us very nice level sets that we can then use in order to control our robots, for example, for full body control, or even for interacting with humans. And we can extend this also for learning for any pose of a human and for any distance, the distance field, as you see, for example, here. And this allows us to query these distance fields from any level and interact with the human and define different level of safe sets that we want to, depending on the level of interaction that we want. But this is a bit on the high level of how we can learn this deep sign distance field, where we introduce some geometric regularization indeed in order to learn these nicely level sets. But we were more interested into learning more complicated interactions and dynamic interactions. So we looked into how we can formulate safe reinforcement learning in a way that we can really take into account the constraints of the problem that we try to solve, whether these constraints are really constraints about, things that you know about your system, for example, about geometry limits, etc., but even constraints that you can learn, like these learned distance fields that you can extract. Now, the problem formulation of safe reinforcement learning assumes that we want to maximize our expected discounted return, subject to some constraints. And in particular, if we consider that we have a control, we assume that our robotic system is a control-affine system with some controllable and uncontrollable variables, and we have also our constraint function. We can construct the constraint function and extract the constraint manifold, which of course also considers some slack variable to also count for the inequality constraints that we might have in our system. Now, the question is, how can we use these manifolds in order to impose safety while we are learning, while we do reinforcement learning? So we take the constraint manifold and we compute the Jacobian of this manifold. And then we can now compute the null space of the Jacobian, and we can use a transformation that takes the original action space of our system, in this particular case, the action space of the robot, that are velocities, for example, on the joint space or anything that you want, depending on how you formalize your system. And you can now map and transform your action space into a new action space that it is always tangent on the manifold. And this is just a graphical representation of this approach. So at every point in time, you are always tangent on the manifold and you don't violate the constraints that you have formalized. And as I said, we can compute Jacobians also for these deep sign distance fields. Therefore, we can add them into our constraint function. And we can learn, for example, some dynamic manipulation in narrow environments like here, taking your hand from the one shelf to the other. And then what is very interesting is that you can transfer now this into the real world because your constraint is always active. So this transformation is always active and you can transfer into the real world without much loss of performance. But more interestingly, we can also learn more complicated tasks, like in this case, in this human-robot interaction scenario, our robot has to deliver this cap upwards. So you have the constraints to avoid the obstacles with the environment, to avoid the set collisions, of course, keep your upward cap, but also avoid the human that continuously acts on the environment without caring about what the robot does. As you can see here, a caveat is that here we use perfect perception, while before we're using a onboard camera to really understand the motion of the human. In this scenario, we wanted very, very good perception in order to fit our sign distance fields to have very, very good evaluation of our SDFs for having the learning process. And we have done this experiment multiple times. Initially, our student was very skeptical about the robot, but then it had seen how smooth the robot was, and it didn't collide at all or overturn the mud. So it became very, very confident. So we were able to do this several times successfully. Now, another important aspect, and I think it touches also to things that we have heard before, is how we can represent different objectives when we want to do, for example, trajectory optimization in the proper topological space. Now, there are different approaches when you do, for example, planning, or where do you represent the obstacles, for example, or your target object that you want to interact with. But the most easy thing when you, especially if you learn from imitation, is to do things in the task space, especially if you have a human demonstrating something happening to objects. So you may have an object-centric representation, and you don't want to really be subject to the configuration space of a robot that you might be using, for example. So yeah, using things in the task space makes things more natural, I would say, for imitation learning. So initially, we were considering to use energy-based models because they can capture multimodality as implicit priors for trajectory optimization, solving planning asynchronous problems. And as I said, we were interested into these energy landscapes because they can capture the multimodality in the data. And they are also composable because they belong to this exponential family. And they can be composed with other objectives that could be appended into like exponential kernel. And then we can represent them in any space because we can use the differential kinematics to actually move from the task space and do like differential IK, go configuration space, and vice versa. Now, while we started with EPMs have they're very complex to actually train. So we quickly moved to diffusion models that can capture the score functions of the gradient of this energy landscape. So last year we tried to extend the works from diffusion models that we know that they started from 2D images into the SC3 space. And we show how to actually do a diffusion process in SC3. Thanks also to work from Greg. We were greatly inspired from his books. And we applied therefore diffusion process, and we found that a very typical scenario where SC3 really plays a role is, for example, grasping. So we represented the, let's say, distribution of possible grasps on different objects by this SC3 diffusion model. And then we can actually sample possible grasp by doing the inverse diffusion process. And what is interesting, and you will see in a while, is that we can leverage these ideas of combining different objectives in order to do gradient-based optimization through diffusion. So this is the model that we use. It's quite simple. We need a point representation, point cloud representation of an object. We need an SC3 representation of the grasp poles, which we present with different points. They pass through some initial layers where our auxiliary task is to infer the SDF of the object that we want to interact with. We take some features, we plot on them, and we try to predict the noise vector. We have done this for a class of objects. And as I said before, if we take the perspective of planning as inference, we can frame the optimization that is originally a minimization problem of some cost function as a composition of different costs. And then we can consider now that we can add there our grasp function, the one that we learned from S3, as a grasp cost function. Now, everything is happening with gradient-based optimization. So here, actually, I don't have the exact equations that you will see in the paper and actually implemented in our code base, but you can use now the differential kinematics, the raw kinematics, to actually map in general to configuration space and vice versa in inverse kinematics. Oops, the wrong laptop. So as I said, now we can frame motion generation as an inverse diffusion process using the stochastic Algebraic dynamics. And with this planning as inference view, we can actually compute our posterior that it is the trajectory that we want to solve. And this is actually very interesting because in this case, you are diffusing through the possible graphs, but also the possible trajectories that lead the robot from an initial state to a final state, or even continue on and do also the placement. And you do this in a single optimization pipeline without needing to just sample initially some graphs, then run your motion planner, and if something doesn't succeed, go over it again and again. And we have shown that with this approach, where we can actually combine our learned objective, the grasp objective, with other obstacle avoidance objectives, etc., you name it, for optimization. We also gain some sort of generalization because we can form the scene differently and still have the robot perform nicely the task. And we have also done a bit more challenging tasks like picking these marks with different configurations while having different obstacles in the scene and trying to place it onto the shelf. Of course, the caveat here is the total planning time, which is, I think, on the range of a second in this case. But this was like early work from diffusion, so we haven't tried different methods like DDIM that would be faster later on. Now, another work that looked into how we can compose different objectives, this I will pass a bit fast, had to do with how we can actually tune in how these weights that get composed change the actual behavior of the agent when it especially has to perform tasks in objects with different dynamic obstacles or very difficult spaces with many obstacles. So again, we consider this planning as an inference perspective. We use Riemannian motion policies as our policy parameterization, and the composition of these Riemannian motion policies can be seen as a product of experts. And we proposed a methodology with which we can actually shoot in an MPC, if you want, style, different parameters, so some sort of meta parameter optimization online of these weighting parameters in order to change in the end the metric to scale up or scale down the metrics of these Riemannian motion policies to allow the agent to avoid different problems. So the one approach, we take a probabilistic approach, and then in the follow-up work, we took an optimal transport approach, which is much faster to solve, but it is deterministic, while the previous one was probabilistic, so you could actually exploit also uncertainty. However, this one is so fast that it can work in milliseconds compared to the other approach where you have to do suiting, etc. And therefore, it can really account for uncertainty in milliseconds. And it was very interesting to see. And you can even do more complicated tasks like almost full body control with some weird targets that my students have defined in this work, only by scaling this weight of the primitives, these Riemannian motion policies that we have defined. Now, I will touch also on the point of equivariant diffusion policies, only that they are not diffusion policies in our case, but they are, I think, lying on the same direction of generative models. So we have been working with diffusion policies, and we have figured out that they are rather slow usually. And when you want to do manipulation, depth manipulation, you want usually to be very fast. You need high frequencies, but you want also your robot to not need millions of data points, right? So you want it to be able to understand and extract special relations so that you can induce generalization. I don't know if I have time to go through it or how much time still. 10 minutes, okay, yeah. So in this work, we combine deep generative models, and in particular flow matching, that we have found out to be the state of the art in generative models and performing diffusion models. And we combine geometry-aware policy representations in order to bring together these two worlds to ensure, on the one hand, the fast action generation thanks to the flow matching, and on the other part, to ensure these desired geometrical properties, like the geometric understanding of the scene. I will not go through the details of the flow matching. just what is to understand is that this approach solves an optimal transport problem when it does the denoising. So it takes some deterministic paths in order to do the denoising from some initial noisy distribution to your target distribution. And as I said, it yields much better performance. In particular, we use the rectified linear flow approach that at the time we were doing this work, it was the state of the art. So we have fast policy inference thanks to flow matching. How do we induce now generalization? So we want to have SC3 equivariance. I think we already now understood what equivariance means. So if you somehow transform your observations in SC3, you want also your actions to also equally translate. Now, how do we do this? We were inspired by works from protein folding. So we took a look about what is happening in AlphaFold, for example, and we proposed a new architecture that can give you equivariant policies. First, we want to understand local spatial relations. So we start with the premise that I think also Robert referred to. We wanted to find a method that will allow us to do invariant transformations in the local ended vector space, that then when you go onto the gradient, the vector field allows you for global equivariant action generation. So we define different frames, the frame of the robot, the frame of different objects. Now, this could be also point clouds. You can imagine that this could be also a point cloud when you have certain registered frames. And you also sample possible actions, so possible end effector frames. So we represent in the end the scene as this pair of poses, and we add additional features on them. So the policy parameterization, as I said, have this local pose representations, and now we design a model that it is SC3 invariant. We call this SC3 invariant transformer, and it uses the invariant point attention layers that was introduced in AlphaFold 2 to actually introduce this invariant transformer. I will briefly explain to you how does this work, how does this changes the self-attention of the normal transformer. These poses that we get can also have some features, which could be, for example, features about texture, features from pre-trained models, whatever you want. It can also have you also have the actions that you sample from your initial distribution, together with some action features that you learn with some encoder, and you have also the K that represents the denoising set. So this goes through. This is an S3 invariant transformer, and the output is basically the change in the pose. So you compute the vector field, which is what we do in diffusion and also flow matching. And you end up doing these update actions quite fast, and you get the final path basically to take you to your goal configuration. Very, very briefly, how does the IPA work? In the keys and queries, it appends additional points. Think of them as featurized point clouds, which can get transformed with respect to the SN3 transformation, so going from one, let's say, pose to another. And then you use some metric on these points in order to impose the consistency. Now, I will not go through all the process, but we have shown how, also in this case, you can start with an invariant model, and by trying to compute the next actions of the delta, so the vector field, you end up with a globally equivariant action generation. So this is the process. You have your initialization of your system, you perceive the scene, you assign your poses, you have your invariant point transformer, then you combine it with flow matching in S3, and you end up with action flow. I will pass through some of the results for the interest of time. And we'll go to the real world results. The key is that this method requires less data as it was expected because it is equivariant, but it's also much faster in inference. And then we have also collected real world data, for example, for bulk screwing. And we have shown how this outperforms just replaying even the demonstration, even if you want perturbation in this demonstrations, and also how this can result in equivariant representations. I will go to this, like how do we do the initial registration? I want to say, but there is not much time because I will not be able to finish talk in time. So we register initially the scene, taking several views. Then we append to specific poses the SC3 pose by considering the rotation to be just a unit vector. And then we apply the our invariant transformer. We do the training here for the map hanging, and then we can see in the test time, even if you move, also in our case, the map, for example, it is quite reactive, the system, and will follow and hang the map. Okay, the last part is actually in the posters, so you can ask Nehal that is studying there. It has to do with SC3 graph generation from any viewpoint. So we took the standard setting of taking point clouds and understanding which is a good and bad graph in SC3, and we used local and global neural surface rendering, which allows us to get quality evaluation at any view because we have mobile manipulators that can move around, have their camera move in any pose, and also a robot can go up and down. It has the elevation, and Nahal can also talk to you about how we can also add graph affordances of semantics in our graphs. And I will just briefly play here the videos that we trained in simulation in the VGN with the VGN data set that we transferred it into the real world. We have done some sim to real noising during training, and this was enough for getting a pretty good performance in the real world in unseen scenarios. And as the last part, I just was talking about how we can understand the scene, but for mobile manipulations, for example, for mobile manipulation, what is very interesting is also how they can use their information about the scene in order to explore efficiently. So in the work that we presented in ICRA, we have presented a MPC style, again, approach that uses RGBD information from the onboard camera of the robot. While it is operating in a scene that it is not known, you have only rough knowledge about an object that you try to find, which is here, in particular case, the banana in this red box. And the robot has to figure out by balancing information gain versus possible grasp executability with respect to also reachability of the robot and the path lengths that they will have to execute. What is the best course of action, which ends up in a performance which is much better than just do next best view. I wanted to show this one, especially if we consider hard graphs, for example, side graphs or graphs where the clutter is quite high, while the next best view approach to zigzag and so on. And we transfer this also in the real world using some object detector. We start initially by trying to figure out what is the object that we try to find, and then the robot starts exploring the scene till it figures a good grasp and a good also configuration of its body with respect to the grasp in order to stop the exploration and execute the grasping action. So yeah, this is work that has been done together with students and colleagues that I would like to shout out to. And I think as a rough takeaway about, I think already the previous talks have put very much emphasis on this. I think geometry and priors can really help us generalize, be efficient, and scale robotic behaviors. And I think we need to inject them also in more large-scale models and try to understand what type of representations they can extract and also consider how we can use the structures that we learn for safe interactions in the real world. So yeah, thank you so much. Yeah, maybe some questions. Janet? Yes.
What do you think about the bitter lessons that they
Yes.
the main message of the yes, maybe in the short run, we think about smart structures, it will help here, but eventually it will not be that simple.
Yeah.
That's what he puts forward. So, which is like very much like that people. I'm curious, like, I would say there's some parallel to it, why this debate issues, the wrong priorities, they may be bad.
Yeah.
But I'm wondering how you think about it.
Where's the fine line? I think, yeah, I don't have an answer into saying that this is the structure of the prior that you should use in any problem. This is why I'm very skeptical about the general purposeness of these models. I think that when you think of problems in a more modular way, you can really find priors and structure that is more specific to the module of the problem that you're trying to solve, and then hope that these are also composable in order to build something more complex. So I think that these are both two hypotheses that we try to investigate as a community. The one hand, more data, infinite parameters, are they going to eventually arrive to the point of learning everything or interpolate in the world? On the other hand, I think there are the people that are interested into imposing these structures in the networks or regularizations to be more efficient. In the end of the day, I believe something somewhere in between will have to happen. Like if you can get more powerful representations from these large scale models, okay, let's use them, but depend them then in some space where the robot will be able to learn fast, because I don't believe that if I put my robot in the house of my grandmother, it will be able to learn a new task fast by my grandmother, for example, showing something. So I think somehow we need to investigate even on if we have pre-trained models, how can we take the feature spaces, because they are also super large. They're also very expensive to use in terms of like inference time, or they can be closed loop, for example, and use these in more small structured models to have faster inferences or be able to update them on a more specific task of interest faster. Other questions?
Yeah, I think we're good.
Yeah, if there is no other question, we can go for the Robert. Yeah. We can.
What was the boxes or boxes or point clouds?
Point clouds. From point clouds, yes.
Good.
How about conclusions?
Yes.
You have to break it. So if you train something and then something way, right? How strong?
In this particular method, probably yes. This is why for doing the initial registration of the pose of the scene, the robot has to, in some sense, scan the scene around and do this initial pose registration. So extract with the point cloud, basically complete a bit of the point cloud, and then pass it through a point net, and so on, and append to its point in the point cloud the information. But I'm very hopeful that this could be combined with the work of Snehal with the neural representation. So basically use some sort of nerves or implicit representations of the scene, and hopefully we can get something even more powerful that doesn't need you to really scan the scene to extract the scene information. Yes.
Yeah. How important do you think Dirk suggests?
Oh, very important. Yeah, I think they are very important. I think it should be.
Or in terms of representation?
I don't know how good Gaussian splatting can be for extracting the representation that we need for close point contact, although there was another parallel talk about inducing like Gaussian plots with physics informed information. I'm very excited to also look into these things. I think though, from the neural completion, at least of what we have seen, if you take into account not just completing the scene, but also what's after, be it the model of the world, like predicting the next state of the world, or in particular, the downstream task that you want to do, I think it will shape the representation differently. So in the graphing paper, because we're training the scene completion with the grasping approach, and together with the grasping approach, we're doing additional local reconstruction of the gripper and the object. This yielded much better features than the decoupled approach. So I think it's very, very interesting to investigate how these models from computer vision and graphics couple with decision making from our point of view for robotics. I guess we can go for the posters, and I'm happy to discuss those outside.
Yeah.
Thank you so much.